As I was kindly introduced, I am export director for Tecnair. Tecnair is a company part of the Luve Contardo group, a group of companies of 1,500 people worldwide, with installations in many countries of the world, including Sweden. As Tecnair, we are the part of Luve. Luve makes dry coolers, condensers, coils. Some of you might know it as Aya here in Sweden for dry coolers. My group owns a company in Sweden. As Tecnair, for data center cooling, for what you're all interested in, we work since 19 years, so very long relationship, with the company TPI, with which we're exposing a unit here today, Mr. Thomas Palmberg, who I thank very much for the time and effort which he does in organizing these beautiful audiences with Data Center Forum. Now, we are based in Italy, so we are Italians, as a mother company. The units you can see here today on our stand, are all manufactured in Italy, in Milan, 20 minutes from the biggest airport. So very, hopefully high quality, Italian quality. Italian prices, so not German prices or not higher prices of the unit. This is something which I particularly appreciate, especially because in this very tough economy, you have to be very high on quality, and at the same time, you have to be competitive in prices. This is our manufacturing plant in near Milan, near Varese, with this is 11,000 meters, of production space, all for close control, laboratories, testing, and anything you might want. Cutting to the chase, cutting to what you're really interested in. This is what we, as Tecnair, through TPI here in Sweden, can offer you for your data center needs. From low density to high density units for close control. Therefore, units as the ones you see in this slide in the areas in the perimeter, bigger perimeter units with the fans in the floor, so to gain space, I'll get more in depth in it, and in-row units, units which physically go in the corridor, in the cold and hot aisle, like the ones we're doing today. I will show you a little bit of the components we can use in the unit, modulating up and down completely the way we use the components, so to reduce costs at a minimum. I will show you our free cooling alternative possibilities, and I will close the presentation before I hope some of your questions by showing you a case study, a situation, a physical installation of 930 units, all in the same installation, not exactly the same weather as Sweden, because it's the Jeddah airport in Saudi Arabia, but anyway, a very, very big data center, which has everything you're seeing here, entire 4 level. So very, very high. Now, this is a slide I always try to talk about every time I have a chance. This is a lengthy chat, quite cozy and easy, about why you need cooling in a data center. I don't know how many maintenance guys or how many of you are actually data center managers, but you know very well that this is a dream. They're never this well made, they're never these tidy corridors, and if you could place an extra server there to make more money off it, you would, immediately. This because the slide to the left and the slide to the right, on this side, have 3 years in difference. I want to point out that in 2011, every minute, some of you might have seen it, have 48 hours of YouTube content go on the web. In 2014, 72 hours. In 2011, Google received 2 million demands a minute. In 2014, 4 million. Etc., etc., etc. But the base of the people which are using the internet has not increased that much, from 2.1 billion worldwide to 2.4. Why am I telling you this? Because when on Christmas Day, all of you are posting on Facebook, Merry Christmas, my friends, when I was on the stand chatting and at the same time checking my emails, everything we do with these things heats up this. every time you're posting on Facebook, every time we're looking at Google, we're heating up the cloud. If any of you have been in the data center long enough, I have worked in Technair since 13 years, you will have noticed that consultants or technicians are always over-designing their data centers. It's always a rack for 100 kW, and then half of it is empty on startup. So what happens? That you design a server at 100 kW, you have 30, 40, 50 kW of heating which is being produced, therefore of cooling which is being demanded. You overspent on a big 100 kW cooling unit, you designed your big cables, etc. for 100 kW, and by the time you are installing the data center in 2012, using it in 2015, you're near already at the end of the life cycle. You've got nice bypasses of air, you've got your fans which are absorbing a huge amount. So what I would like to show you from now on these next slides is let's try and buy, whether from me, whether from Stulz, whether from Schneider Electric, from the good manufacturers which are out there, because trust me, I just named good ones. There are quite a few bad ones as well. Try and buy a unit which is future-proof. A unit in which even my mother could go on the microprocessor and use it easily. Even my dog possibly, but that's another question. Why? Because everything you see on this microprocessor has to be graphic, has to be easy to read. And as you can see in these slides, yes, it's graphically nice and shiny. And you can see the percentage of use of the components. You can monitor the hourly, daily, weekly, monthly use. But most of all, everything which we install in our unit, and I'm sure all the best ones do it as well, is completely modulating. This means that the valves have got to be three-way or two-way modulating valves, because they will give me an energy efficiency in the long run. The fan, we'll see it on the next slide, has got to be modulating as well. And I've got to start using all these components together, so that when you buy your server, and you're not using it at full capacity, but you're using it at half capacity, you're also using the unit at half capacity, and you're absorbing less, etc. Let's get to a physical example of a modulating fan. Now, with our Technair units, the electronically commuted fan is completely standard. All our units, from the smallest 5 kW to the biggest 300 kW, all have electronically commuted fans. These fans allow me to work in three ways, as everybody has always done, just by letting them run at their maximum airflow, constant airflow working logic, or in a data center, much more useful, having them run at a constant pressure. Probably your data centers demand 50, 70 PA of available static pressure throughout all the floating floor. That can be also done. The fan regulates itself, turns faster and lower according to the pressure or the airflow you want. The third system, the one which I brought here as an example, these are Eurovent certified data, by the way. Everything I'm showing you has been certified by an outside agency. This is especially important for us as Technair because we're Italians and we had Berlusconi as a prime minister. So we're not exactly trustable for our politics, we are trustable for our units. So we went to the French. I know it sounds like a joke, Italians going to the French, but Eurovent is French. We went to them and they certified our units at the time, in 2011, and also our data. So what you're seeing here is not done by us, but done by someone else. Now, in the first example which you're seeing, I'm letting my electronically commuted fan on a 145 kW unit run at its maximum airflow, 26,500 meter cube per hour. At this working logic, just let it run at its maximum speed, which is what most data centers work at. I have a cooling capacity of 145 kW, an energy efficiency ratio of 18.5. Each fan consumes 5.48 kW. The annual energy consumption of the fan is 48,000 kW. And the average cost is, on a year, 5,600 euros. Just by letting the fan run. This is how a unit by us, if you just switch it on and let it go, runs at 145 kW. If instead I let the unit run, and if you buy our unit, it's already standard, what I'm going to say. It's just a question of changing the software. If we let the unit run in a constant cooling capacity, therefore, if I have 24 degrees set point and I give it a minus or plus 1, I let the unit run no matter what between 23 and 25 degrees. If it's lower than 23 degrees, 22.9, it means it's very cold in the room. I can slow down the speed of the fan and still maintain my cooling capacity. If it's 25.1, it's too hot. I can increase the revolutions of the fan. I am Italian, I've got to use my hands. 25.1, it's quite hot. Increase the revolutions of the fan and let it give a little bit more cooling. I've been very simple in this analysis I just told you, but what I'm doing is increasing or decreasing the revolutions of the fan according to the temperature and the cooling capacity in the data center. This means using the fan, which costs money to run, only how and when I need it. By doing it like this, and now comes the numbers, I am allowing the fan to go not at 26,400 meter cube per hour fix, but to slow down and go back up, down until 16,500 meter cube per hour. My cooling capacity is still there, 145 kW, and my energy efficiency skyrockets to 53.20. Most of all, my fans, instead of being at 5 kW, are at 1.8. My cost of running the unit like this is 1,928 euros instead of 5,616. It's 65% less. I'm just stressing the point that any Technair unit, any good manufactured unit can already do this out of the box. It's just a question of going on the microprocessor and modifying the parameters and accepting the logic. You can tell your customers, the guys running the data centers, look, change that parameter, you can save 65%. He will be very, very happy, your customer. And if you guys are data center guys having and running your data centers, try looking if the units you have there, whether they're Emerson, whether they're Stools, whether they're Technair, if they already have this feature in. Because it comes in handy. It's energy efficient. And since we have it standard since 2012, I'm pretty sure some others have it as well since a long time. Let's take what I just told you and bring it on another level. When I started this business 13 years ago, everybody was talking local networks, redundancy, N+1. That pretty much meant that if you have a data center of, let's say, 200 kW, you bought 5 units of 50 kW, one extra. Or you bought 3 units of 100 kW. Anyway, you gave a little bit of redundancy. If you have a 50 kW data center, you buy 2 units of 50 kW, one runs and one stops. And every 12 hours, you switch one on and one off for safety. This is normally how data centers have been done. Now, by taking what I just told you about having the fan go up and down according to need, by having only modulating components inside the unit, instead of being in the situation on the left, in our standard local network, just imagine this is a data center for 100 kW. You have 2 units for 100 kW, one here and one here. If I have one off and one on, and at midnight and at midday, I switch them, I have one fan, this one, which is running at full speed, one coil which is running at its maximum condensation and its maximum airflows. I have a compressor which is at its maximum, or the three-way valves, etc., etc. Plus, imagine it's not going to be exactly balanced in this data center, is it? If instead I have a modulating fan, simple chilled water unit, I have a modulating fan, and I switch to what we call SmartNet, because it's nothing more than a smart way to use your local network, I can have both units running at the same time at 50%. I still have my redundancy, because if for any reason I was to lose this unit, this one could ramp up at 100%. But what's the advantage here? A better balance of your data center, lower noise. Not that noise is a huge issue in a data center, but it's become a huge issue if you have your customers going in, if you have a maintenance guy, etc. Because two fans running at 50% are 20% less noisy than one fan running at 100% for double the airflow of 50. Noise is one of those funny things which nobody understands, unfortunately, or fortunately. The way we see it is that you're already buying the two units. You're already installing the two units. Use them both. You still have your redundancy. We have installed this software since 2012. We have standardized modulating components since that very same year. These are 4 units, exactly the same as the single one I showed you before. Same model for 145 kW. This time, therefore, we're taking 79. In case number 1, we have 4 units. 1 is off and 3 are running. When 3 are running, they're running at 79,000 meter cube per hour, and they're giving 436 kW. The cost of running it like this is 16,849 euros, based on a cost of 0.1170, by the way, cents of a euro. If instead I switch on the 4th unit, this is plant number 2. If I switch on the 4th unit, the other 3 units will have to slow down. I don't need to use them at the same level. They can work less, harder, soft, run at a lower speed, make less noise, and yet they're giving me the same cooling. At 75,600 meter cube per hour, so 4,000 meter cube per hour less, I am getting more cooling capacity, 456 against 436. Why? Because our coils all have a filter. They're all placed in a certain position. They all will have dead zones. They will have less efficient zones. If we use all the units together, I'm obtaining the maximum from all of them, the most efficiency from all of them. My fans will absorb less, the cost will be lower, the noise will be lower, the cooling will be even more. The cost of running it like this is 9,796 euros. 42% less. Again, I'm not telling you buy a new unit. I'm telling you, since a few years, most manufacturers, most good manufacturers, have standardized these features. If you think about a data center, most often there are units, there are data centers which have to last 10, 15, 20 years. But after 5 or 6 years, the technology develops so much that you have to change everything. And you might still be using close control units from 20 years ago, or from 15 years ago. My old distributor in France, we don't work with him anymore, decided to change because his customer didn't have the money to retrofit, to place new units in. He changed units with R22 refrigerant to R410, changing the pipelines, not changing the units. I told him, you're crazy. You're spending 70% of what the cost of a unit would be to get a unit which in 3 years you're going to blow out of a room because it doesn't do the efficiency, because you don't have all these things. He told me the customer doesn't want to pay the new units because he's physically happy with those, and he says that in 5 years they're anyway changing the data center. I am pretty sure that if they had made this calculation, they would have seen that in 3 years they would have paid over the new units easily. Very, very easily. I obviously now talked more about the fan. We can obviously do a unit also in direct expansion, completely modulating. This means that if on the chilled water side I'm using 3-way modulating valves or 2-way modulating valves with my modulating fan, on the direct expansion units, our direct expansion units, like the one there is here on the stand, have an inverter-controlled DC brushless compressor, one which does not break, because inverters have a bad tendency of giving problems. DC brushless have a very high reliability, and integrated in it an electronic expansion valve. The electronic expansion valve, together with this, allow me obviously to go down in cooling capacity, thanks to a modulation of the speed at which the scroll compressor, which is standard, turns. we limit it for safety and evaporation limits and safety issues to 50% of a nominal airflow. And we link it by 10% to the airflow. This means that if the unit can give 100 kW at 20,000 meter cube per hour, the compressor can maximum go down to 50 kW, and the airflow can maximum go down to 5,000. We don't let it go further down than that because we might risk freezing on a direct expansion unit. These are some more things in your cases which I think you need to always look at. Getting back to the physical part of a unit now. We have, the market has normally 3 types of cooling systems for CRAC units, computer room air conditioners. The first one, the standard one, is the classic up and down flow units with the fan integrated in the series, which have all the characteristics I just showed you: modulating fans, inverter compressors, electronic expansion valve, three-way modulating valves, etc. Our range goes from 5 to 100 kW in DX and from 10 to 200 kW in chilled water. Something which instead I would like to bring the market up to is what is happening in England, for example, where I was 2 weeks ago. There, the data center of American Express, which we supplied units to, has a floating floor higher than this one, 1 meter. 1 meter of floating floor. Because they say there are so many cables. Now data centers are going further and further to up solutions, everything on top. But there is also the possibility, and this is what this unit is for, to use the floor and drop the fans in the floor. So effectively, what you would get from a solution like this is a higher unit of 2.5 meters, only that the fans will go in the floor and therefore are not perceived by your customer. Why is this important? Because if we were to go back to that slide I showed you before of a big data center, you don't have width in a data center because you've got your servers. Often you don't have height because you've got cables going around, but very often you have floor. And the more the floor goes up, the more things I can place in there. With this solution, by the way, the noise goes down. The efficiency also goes up because I have a unit with a fan in a free field. And most of all, my cooling capacity can go up as well. These units, which we call the G series, have a cooling capacity of up to 180, 200 kW in DX and 300 kW in chilled water. Why is this unit more important to Sweden? Because I'm not just doing a standard presentation. I'm also, and I hope to be able to answer a few questions after, trying to place it on yours. Because classic computer room air conditioners like these ones were made with water 7, 12, and 24 degrees. That is a way a little bit old of seeing your data center. Data centers right now, Infinity in the UK, Verizon in the UK, Telecity in Finland, for example, all have a much higher temperature controlled on the hot corridor, 38 degrees. And the water, instead of being at 712, is at 2028. If you work with water 2028 and air at 38 degrees or 39, so delta T10 or 11 fixed, you're using a smaller chiller, a smaller pump, more efficiency on the whole system, and most of all, you have to have a unit designed on purpose for higher temperatures. You cannot just switch water from one side to the other. The overall effect of using higher water temperatures is just a follow-up to what Ashre has always been saying since 10 years, that data centers, since 2008 in the strongest form, data centers can work easily up until 40 degrees. The last solution, the one we physically have on the stand today, on our booth today, is an in-row unit. You've probably all already seen it. There are two in the forum, one opposite side to the others. Ours is the one which doesn't have lights. These are units, and it's a very good spot cooling system, which go between the computers, between the servers, and is perfect as a solution for newly designed data centers. Data centers which have the complete luxury of being able to be built from the ground up. So no perimeter, a good calculation of the cooling capacity from the beginning, racks which are designed to their specs, etc., etc. We have both direct expansion and chilled water available in this scenario. The maximum capacity which we can give in the 600 centimeter structure, which you even see here, is 40 kW. But these, as you're seeing in this slide, are units which physically go, quite a few of them, in the same corridor. Now, this which you're seeing here, let's try to bring it up to something similar to what you're normally seeing every day, is a data center with, as I told you, Jeddah Airport. Jeddah is in Saudi Arabia. It's the closest city to the Mecca. If any of you, I don't think so, have ever been, but anyway, if any of you are Muslim, it's their Vatican City, to give you an idea. It's their biggest religious place. They have they have an airport so big that they want to manage, and that's totally crazy if you ask me, 30 million people a year in that airport. The outside temperature of that airport is 55 degrees in summer and 25 degrees in winter, just like Stockholm, identical. And as if it's not enough, challenge, 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 we love challenges, they asked for seismic tests of the unit, which are totally useless because the unit will stay there and the airport will already be crumbling. But anyway, they asked for that. And as if it's not enough, in the airport there is a disaster recovery center for another center of, you know when in the airports they build banks, commercial centers, and business cities with offices, there's a disaster center for that as well, all in. Practically 930 units, of which 200 in Tier 4 and 630 in Tier 3. The Tier 4 units means double electrical connections, automatic transfer switches, double cooling, a chilled water unit with inside a direct expansion called for safety, etc., etc., etc. This is how the data center looked before the servers arrived. To give you an idea, this room is 10,000 meters squared. It was difficult to get it all together in one angle. And the air, as you all know, comes from the floor, so taken from the top and back into the bottom through these grills. Funny story, these guys doing the maintenance slept on the grills during their breaks because this was not yet an air-conditioned room. It was 45, 46 degrees outside with no air conditioning in the building. So here you had our test air coming at 35 degrees. They were sleeping on it because it was 10 degrees cooler than the rest. Pretty funny. This is how it looks after they installed the servers. Not your paradise, if you ask me. Unfortunately, all these units have a space of 1 meter in front of their UPSs, their racks, etc. It's a labyrinth in there. But the end result is a perfect isolation of the hot and cold corridor with an energy efficient, a PUE, I apologize, calculated obviously on the whole of the data center at 1.8. Why is it at, at 1.18? 1.8 was a little bit too high. 1.18. Why is it at 1.18? Because, as I told you before, their water temperatures are 28 with 39 degrees in this hot corridor. They are effectively using the units as little as at their minimum speeds, so to be able to have the least cost of running the units all together. The cold corridor obviously goes a little bit up because if you use your data center on the hot corridor at 39 degrees, you will have 26, 27 degrees in your cold corridor, but stable What kills a rack, what kills a server, I'm pretty sure you know, is not the very high temperature, is the changing of the temperature and most of all of the speed of the air, especially on the switches, which need to have constant speed throughout. So this is why having between 24 and 26 degrees, there is very little change in the cooling of a data center, but the efficiencies of it all are very, very different. We are in Stockholm. We're not in Jeddah. So let me finish off by showing you what we consider, and with TPI we had good success in installing these units in Sweden and in the whole of Scandinavia. We propose a free cooling solution with intermediate fluid, which is water, by using an outside dry cooler, and in our unit we have a 6-row coil. Our standard units have 4 or 5 rows. We use a 6-row coil with 3 rows water coming from the dry cooler, and 3 rows direct expansion. So very simply, I'm just going to do you a physical example. We have 3 working modes you could simplify to. We have a mode with total free cooling, winter, a mode of partial free cooling, middle season, autumn and spring, and a season of no free cooling, a mode of no free cooling. The no free cooling is summer. Physical example, 24 degrees set point, 19 degrees, 5 degrees delta T, means up until 19 degrees outside, I am totally in my free cooling mode. My dry cooler is sending water into the unit through a water-cooled condenser, which is completely bypassed, and completely towards the water side. The only cost of running this unit in any temperature, by my example, below 19 degrees, is the cost of running the fans on the dry cooler, the fans in the unit, and the pump, which makes it circulate. So today, the only cost would be the fans and the pump. In Stockholm, in Sweden, you would probably be in this situation 7 months a year, 8 months a year, probably. When 19 degrees arrive outside, I start opening a freeway valve and sending water partially towards a water-cooled condenser, which cools down, as you can see here, the refrigerant, which is then sent back to the coil. This means that from 19 degrees until 24 degrees, I am helping the water side with direct expansion. The more I approach 24 degrees, the less I'm using straight dry cooler water to the coil, the more I'm using direct expansion. When it's more than 24 degrees outside, I have no free cooling benefit, and I'm completely in direct expansion. Obviously, colder climates or tempered climates have a very high energy efficiency by using this modulation system, because we are effectively only using pumps and fans as many months as possible. I will never sell this unit in Spain. I will never sell this unit in Abu Dhabi, Dubai. Italy is not a big market for free cooling. Belgium, Germany, Denmark, Sweden, Finland, Norway, Lithuania, all of them are very big markets for this system. What's the advantage of this system when compared to other free cooling systems? Some of you might be knowledgeable on direct air free cooling, which pretty much means having a damper, which when it's 19 degrees outside, opens and drags the air straight in. The problem of direct air free cooling is that the filters need to be changed every 4 or 5 days, every week, because they will become dirty. If we were doing direct air free cooling today here in Stockholm, and if you had a road next door, the filter would get dirty. Here there is no outside air coming in. We're using the outside air to cool down water. Very energy efficient, very green, because it's still a green system, and no costs, operational costs in maintenance. This is the end of my presentation, and we have, I think, 2 minutes to spare, a few more. And if there are any questions or anything, I'm on the stand or here. Thank you very much for your attendance.